So in our previous video, we talked about 5 important surfaces that come up throughout multivariable calculus. And the first of those surfaces was the paraboloid. So we're going to focus in on that one today and look at some examples around graphing paraboloids. So first thing we're going to do is define what's called a trace. So you could say a trace is the intersection of a surface with a plane. So I'm just going to use the symbol here for intersection. So we take our surface, we intersect it with a plane, and the curve that we produce is called the trace. So this is especially useful when the plane is something like the plane x equals 0, y equals 0, or z equals 0. In particular, that's when we talk about using a trace, and really helpful when we're making graphs of surfaces, especially at the beginning, to think about a trace or the various traces of the surface. So for example, let's say we wanted to graph our familiar paraboloid, z equal x squared plus y squared. And we're actually going to do 2 examples, so I'll show you 2 perspectives on how to do this, but for this first example, we're going to do this using traces. So here's what this would look like. Okay, well, we would say, let's set x equals 0. So if we set x equals 0 into our equation here for z, the equation would become z equal y squared. All right, so let's look at what this trace looks like geometrically. So let's think about 3D space. Remember, x-axis is coming out of the page at us, y is going to the right, z is going up. And so if we talk about the points where x equals 0, then we're talking about the points that are flat on this page, and we're producing a shape that looks like z equal y squared. Okay, so that's a parabola opening upwards in the positive z direction. So we get that sort of shape in the yz plane when x is equal to 0. So that gives us one perspective on our surface. That's saying this curve here, this parabola that we've drawn, lies on our surface. But we could think about the other traces as well. So we're going to see what happens when we set y equals 0. We're going to see what happens when we set z equals 0. And that's going to give us more information about what our surface looks like. Then we can put all that information together into a nice sketch. All right, so let's think about what happens when y equals 0. If we do the algebra, our equation z equal x squared plus y squared would collapse into z equal x squared. So let's draw our x, y, z axes and try to imagine what that looks like. So when we say y equals 0, we're now talking about the xz plane. I'm just going to shade that in for a second so that we can visualize that. So the xz plane in our picture looks like this. So all these points here where y equals 0. So we're not moving to the left of the xz plane. We're not moving to the right of the xz plane. We're just exactly on those points there where y equals 0. Right? And z equal x squared is a parabola that's opening in the positive z direction. So that is a parabola in the xz plane. So that gives us another perspective on our surface, z equal x squared plus y squared. So let's do one more. If z equals 0 in our equation, then that's telling us that 0 equals x squared plus y squared. And if we think about what points x, y, or what values of x and y can satisfy that, there's only one option. X and y would both have to equal 0 in order to make that equation true. Because if we chose any non-zero value for x or y, we would end up with a contradiction here. Okay, so let's see if we can graph that then. Z equals 0 just consists of the points in the xy plane. And if we're saying that x and y also have to equal 0, then we're really just talking about the origin here. X, y, and z all have to equal 0. So we're just getting a single point in the xy plane. Okay, so now we try to put this all together. We've used the traces to think about our surface effectively from a few different angles, and now we put it all together. So we know that our surface contains this parabola here, in the YZ plane. We got that from our first picture. It also contains a parabola in the XZ plane. We got that from our second picture. And then in the XY plane, it just contains that single point there. All right, so if we were to draw a circle passing through the top here, that gives us now our standard picture of what's called a paraboloid. So z equal x squared plus y squared is a paraboloid. It is a bowl that's opening upwards in the z direction, just a hollow bowl. So we're just talking about the points that lie right on the outside of that bowl. And I'll just shade in all those points there so that you can visualize those. So that's our paraboloid. Z equal x squared plus y squared is a multivariable function, and the set of points that lie on that multivariable, or that satisfy that multivariable function when you actually plot them, produces a surface. That specific surface is called a paraboloid. So let's think about a second way of visualizing this paraboloid. So we're going to define what's called a contour curve. And a contour curve is really a specific type of trace. So it's still a surface intersected with a plane, but it's going to be a specific type of plane that we're using for the intersection. Specifically, it's going to be z equal a constant. So contour curve, specific type of trace. It is a surface intersected with a horizontal plane that looks like z equals c. Okay, so for our example here, we're going to graph the same paraboloid as we did before. So z equal x squared plus y squared, but this time we're going to do it using contour curves. All right, so what that looks like, we're going to choose a few different z values. I would say just probably doing 2 or 3 would be enough, and I'm going to choose some numbers that work out nicely. So let's think about what happens when z equals 0. Think about what happens when z equal 1, and we'll also think about what happens when z equal 4. So we're going to sub these different z values into our equation for our multivariable function. We're just going to see what happens to our equation. So when z equals 0, we get 0 equals x squared plus y squared. And we could think of that as a circle of radius 0, if we want to think of it that way. So it's a circle centered at the origin of radius 0. In other words, it's just the origin that satisfies that equation. Okay, now if z equal 1, we'd have the equation 1 equal x squared plus y squared. So that is a circle of radius 1. And I'm going to start to draw a picture here so that we can see how this information is useful to us. So somewhere down below here, let's draw our x, y, z axes. So we're thinking about what our surface looks like at these various values of z. And we've already got 2 pieces of information. We know that when z equals 0, we're getting just the origin. So we're just getting that point x equals 0, y equals 0. At that level where z equals 0. Now, when z equal 1, we're getting a circle of radius 1. So let's identify where z equal 1 is. It's here. And imagine drawing a circle of radius 1 at that z level. So circle of radius 1 centered at the origin at that level of z. Okay, now at z equal 4, we get 4 equal x squared plus y squared. So that is a circle of radius 2. Again, centered at the origin. So we can pick out where z equal 4 is, right here, and then at that z level, draw what looks like a circle of radius 2. Okay, so maybe something like that. So if you were to do this for all the different z values, what you would see is that as z increases, you get circles of increasing radius. So if you were to now try to draw a picture of the surface, try to draw a picture of the surface passing through all those points, you would get this paraboloid, which is just a really fancy way of saying this bowl shape. So when z is negative, you get no points that satisfy that equation. Therefore, there are no points on the surface below the xy plane. So that agrees with our picture. If you had chosen a different z value, like say z equal 2, you'd get a circle of radius root 2. And so you could draw infinitely many of these contour curves. For the paraboloid specifically, each contour curve is going to look like a circle with a different radius. Now we'll do some examples in future videos. We won't always be looking at a paraboloid. So in general, contour curves will not always be circles, but for paraboloids, all the contour curves will be circles. So a contour curve is just a way of slicing through your surface horizontally, tells you what curve is produced at that Z level, and then putting all that information together. It gives you a way of drawing your surface. So to finish up this video, let's talk quickly about some transformations of paraboloids, because once we know how to graph the classic paraboloid, then we can quickly graph a wide variety of related paraboloids. Okay, so if someone gives you the multivariable function z equal x squared plus y squared, we should now know how to make a very quick sketch of that. So there's our paraboloid. It's got its vertex at the origin there, and it's opening upwards. So let's look at, say, 4 transformations of this. Let's say someone gave us the function z equal 1/2 x squared plus y squared. Well, that is a vertical compression. It's just making each of our z values smaller by a factor of 2. So that's going to result in a bowl that's just a bit flatter. Still got its vertex at the origin like that, but z values are smaller than they were before. So you're going to have a wider, flatter bowl as you draw this picture. Okay, now if we were to take z equal minus x squared plus y squared, think of that as a vertical reflection. So that bowl is now being flipped upside down, still got its vertex at the origin, but it's now opening downwards. Okay, so we talked about vertical compression. We've talked about a vertical reflection. You could see something like z equal x squared plus y squared plus 1. So that's just going to be a shift in the vertical direction. Every point on that surface is going to get moved up by 1. So instead of having vertex at the origin, it's going to now have vertex at 0, 0, 1, where z value is 1. So we could draw our paraboloid like that. And then maybe one other sort of transformation is just changing the roles of the variables. So if we had something like x equal y squared plus z squared, might need to think a little carefully about this. So it is a paraboloid, but the roles of the variables have been changed. See, now we've got x on the left side. X is playing the role that z was playing before, and then it's the other 2 variables that are being squared. So if our classic paraboloid had z on the left and that paraboloid was opening in the positive z direction, then we should be expecting this paraboloid to open in the positive x direction. That's exactly what's going to happen. So the bowl is going to be opening this way. Okay, so now we're comfortable, hopefully, with making a quick sketch of our classic paraboloid, which we got up at the top of the screen. And then we can do things like a vertical compression or stretch, which we did here. We could do a vertical reflection in the z direction. We could shift in the z direction, and we can even change the roles of our variables so that we have this paraboloid opening in a different direction. Thanks for watching.